one time or another, we've all experienced it. The urban driver's nightmare, with all its impacts. Personal frustration, costly delays, tensions. Fuel wasted as motors idle and air pollution mounts. Buses held up, passengers losing time. Bicycle riders endangered. Trucks waiting, cargoes delayed, drivers falling behind schedule. More chances of accidents as cars, trucks, buses, taxis, bicycles, and pedestrians compete for the right-of-way at intersections. There are real tangible costs when traffic signal systems don't work at their best. When they do work at their best, the traffic signal is an impartial referee, setting the rules, helping all roadway users take turns in negotiating the intersection safely and with a minimum of delay. And when traffic signals are well coordinated, the result can be a smoother, more continuous flow for all roadway users, greater safety, more efficient use of fuel, and less pollution. Keep in mind that the traffic lights you see at the intersection are only the tip of the iceberg. The bulk of an effective traffic signal system lies behind the scenes, where professional traffic engineers do their jobs. This film aims to provide an understanding of the traffic signal systems they design and operate. At the heart of everything is signal timing. One of the key elements of signal timing is the signal cycle, which is the complete sequence of signal indications, changing from green to yellow to red and back to green again. Within the cycle, each signal indication of green and yellow allocating the right-of-way is known as a phase. The more phases, the more delay, and of course, there is only so much time that can be provided. A signal timing plan sets the duration of the various phases and of total cycle. A cycle may be as short as 40 seconds, or as much as 120 seconds or more. And the timing plan fixes the duration of the phases within the cycle. Here, more time is allocated to the green for the main street traffic, with less time for movement of traffic on the cross street. When timing is set on a pre-scheduled basis, the duration of the signal displays in each cycle is fixed. It is the same limited amount of time for each cycle and its phases, regardless of the traffic demand. Intersection timing may also be on a traffic-actuated basis that adapts the length of green displays in response to varying traffic demands. Here, a wire loop detector embedded in the approach to the intersection is activated by vehicles passing over it, sending electrical impulses to the roadside detector electronics and triggering action by the controller to change the traffic signal to green. This method automatically adjusts the green time to the traffic demand at a given moment. Activating the signal displays is the job of the controller equipment. For a pre-timed controller, this may be the older electromechanical type, or especially for traffic-actuated control, it may be solid-state electronic type equipment. Signal controller manufacturers now provide microprocessor-based controllers to achieve intersection control at less cost and with less maintenance. It's a relatively simple matter to develop a timing plan for an individual intersection, and even for a series of intersections if the traffic on an arterial is in one direction. For progressive traffic flow, the signals are programmed to establish a definite timing relationship between adjacent signals. This relationship is termed an offset. It's a much more complex problem when there's a two-way flow. Perfect progression in both directions can seldom be achieved. It's far more complicated still to time for progressive traffic flow in a network of intersections. Further complicating the problem, Different timing plans are needed for different times of the day, during rush hours, for example, with their peak traffic flow. And these timing plans will need to be revised frequently because of changing traffic patterns caused by construction and development projects, the redesign of old streets, and the building of new ones. Fortunately, modern computer technology is helping traffic engineers develop timing plans and keep them up to date. Several computer programs are available to aid in timing plan development. One of them, Transit 7F, was developed to optimize signal timing and has been implemented in many jurisdictions throughout the United States through the Federal Highway Administration's National Signal Timing Optimization Project, known as NSTOP. California's program, for example, conducted in 41 cities, showed these results for the first year of testing. Vehicle stops and delays were reduced by more than 14%. Fuel use declined by 6%. Speed or travel time improved by an average of 6.5%. The estimated total annual cost benefit was $31,900,000. Since the project cost was only $2 million, the benefit-to-cost ratio turned out to be a very substantial 16-to-1. Just imagine the scale of benefits if traffic signal systems were optimized in all urban areas across the nation. Timing plans and computer software are the brains of the traffic signal system. The brawn is in the hardware, the equipment and machines, the cables and wires that carry out the instructions. In a number of cities, especially in downtown areas, the older type electromechanical-based systems may be found. The master controller acts as a 7-day clock, sending out electrical impulses that activate a limited number of timing plans by time of day and day of week. The actual timing plans are set at the intersection, where a technician adjusts the timing dials. But just as in so many other kinds of municipal activity that are now computerized, today's cities are moving toward computerized signal systems in order to do a more effective job of managing street transportation. In computerized signal systems, detectors at intersections register current traffic information and feed it back almost instantaneously to a control center. Here, the information is quickly analyzed by the computer, and appropriate new timing instructions are transmitted to the field in rapid response to changing traffic demands. The control center is the command post for the computerized traffic signal system, the point where timely information about system performance comes in, where operators are alerted to signal failures and other problems, where steps for remedial action are taken, and where new timing instructions are cranked into the system in response to changing conditions. An almost infinite number of timing plans can be set from the control center to accommodate the major changes in daily traffic patterns, such as the morning peak hours, the evening peak hours, and so on. Typically, about 8 timing plans will be set in a computerized system, and special timing plans can be called up almost instantly in emergencies that affect traffic: a fire, a serious accident, or a broken water main. Computerized systems are very cost-effective. For example, one study has shown that for each dollar spent on computerized signal system improvements, 9 vehicle hours of travel time can be saved. In addition, about an 18% improvement in travel time can be expected when a computer-controlled system replaces an interconnected pre-timed system. From software to hardware, a traffic signal system is only a structure, a tool. It takes on life only through the activities and dedication of the staff people in using that tool. The staff applies professional expertise to the development of timing plans and patterns to meet changing needs. And both engineers and technicians keep a sharp eye on the operations of the system, monitoring performance, ready to act when something goes wrong. Often enough, something does go wrong. In one major city without a computerized system, it was estimated that at any given moment there were problems at fully half the intersections. Malfunctions at intersections show up immediately in a computerized system. The operator can quickly confirm and diagnose the problem and take corrective action. For example, the problem might be a defective controller unit. In cases like this, the technician may repair it on the spot, or he may take the faulty equipment back to the maintenance shop. How much staff and budget are needed to operate and maintain a traffic signal system? That varies widely, depending on a city's size, its geography, and the frequency with which timing plans are updated. What counts critically is that regardless of city size, the traffic engineering budget must be fully adequate for the job at hand. Large enough for the signal system to be operated effectively with modern equipment. One thing the professionals know, nothing stands still in the world of traffic signals. From the earliest days of traffic control, there has always been a push for more knowledge, more effective and responsive equipment and systems. That's why pioneers in the profession keep upgrading traffic signal systems. And that's why the Federal Highway Administration sponsors research studies and makes the resulting information, software systems, and training courses available to states, cities, and counties for their use. For use is what all the effort is about, helping communities put advanced equipment into operation, update and optimize timing plans, modernize master control centers. As this happens, step by step, our cities will approach the urban driver's dream of the ideal traffic signal system.
Like clockwork.
Smooth sailing.
Great.
Beautiful.
How's that for timing?
Come a long way to today's traffic signal systems, to the new methods, advanced equipment and coordination, to digital computers, real-time traffic responsive control, high-speed communications, instant feedback. All the current technology and concepts designed to keep traffic flowing smoothly, safely, with the least delay. What does it take to manage the complexities of today's urban traffic? This video is an update on some of the choices in urban signalization, a review and a reminder of the best current practices as a guide for decisions. Start where the action is, at the intersection. Here, the older electromechanical equipment with its timing dials is still being used, but increasingly it is giving way to centralized computer control and sophisticated microprocessor-based controller assemblies. These are adaptable to both pre-timed and traffic-actuated control. In selecting and transmitting timing instructions to the signal displays, any type of controller unit can be linked to a computer control center through a controller interface unit. The CIU takes the central computer's instructions and translates them into commands the controller unit recognizes and responds to. When traffic conditions change, or when something goes wrong, detector failure, for example, there is quick feedback to the control center, alerting staff to the need for corrective action. The computerized system, through hardwire interconnections, can govern the timing of arterial streets or of a network to promote progressive traffic flow. But now, in areas where installing conduit might be too costly, or when simple computer control may not be appropriate, it's possible to achieve signal coordination without a hardwire interconnection between intersections through a time-based coordination system originally developed by the Federal Highway Administration and now available from a number of manufacturers. The time-based coordinator contains a highly accurate crystal-controlled clock that maintains a constant time relationship between intersections and interfaces with any type of controller unit. Synchronized timing plans are set at each intersection to provide coordination. With no interconnecting cables between intersections, installations are completed quickly and at very low cost. One project in Virginia demonstrated that a time-based system was installed at a cost savings of 14 to 1, compared with an equivalent hardwired interconnected system. But although time-based coordinators can provide progressive traffic flow, timing plan changes must be made from each intersection, and there is no feedback to a simple computer and no quick, easy way to detect malfunctions and update timing plans. Where there are communication links, feedback, of course, is a key function of detectors installed in intersection approaches as part of a traffic-responsive computerized signal system. Inductive loop detectors are preferred over other types because they accurately sense the presence of vehicles, yet can be purchased at low cost. For most applications, a 6 by 6 foot loop size is considered optimum for computerized system control. Loop detectors must be carefully installed to ensure proper operation and to minimize maintenance costs. Detailed guidance on this can be found in the Federal Highway Administration's Traffic Detector Handbook. How effectively can the system respond to changing traffic conditions? In large degree, that depends on the quality of the telemetry system linking the intersections and central control. There are many options for getting messages through in both directions. Overhead wire is generally less expensive to install and maintain. In contrast, underground cable is more expensive, but more reliable and more secure. Both options may be leased from telephone companies and utilities, or they may be city-owned. Leased lines usually have a lower life cycle cost than city-owned lines, but the city doesn't have full control over maintenance, nor over future rate increases for leasing. With a large number of controllers and detectors scattered over a widespread area and linked to a control center, a large number of hardwire conductors is needed for communications between intersections and the central computer. Use of the multiplexing technique allows the capacity of a single pair of conductors to be shared by several transmitters and receivers. Large volumes of data thus can flow between intersections and the control center, using far fewer wires and at great cost savings. Still other options are emerging. Microwave transmission can be especially useful over long distances, in freeway control systems, for example. And the new fiber optic technology has a great potential for carrying large volumes of data with no interference. In the control center, computer peripherals enable operators to monitor the system as a whole and in its parts, and take action when needed. Wall maps are useful for displaying system status information and for explaining the operations to citizens. However, they are relatively inflexible and costly to adapt to changes in the system. But as technology has developed, the CRT terminal with its speed and flexibility is becoming the main form of display. At the flick of a finger, the operator can call up such information as equipment failure reports, measures of performance, and reports on timing plans. The terminal is also an input device, and instructions can be transmitted to respond to malfunctions, change timing plans, or otherwise control the signal system. A CRT with graphic capability can display all these types of information while showing intersection geometrics for networks. Arterials, or single intersections. Some computerized signal systems use a control panel. This allows the operator to control the system easily through the use of push-button switches. One disadvantage: the control panel is less flexible than the keyboard, requiring physical modification for changes to the system. The hardware grows ever more sophisticated, but what makes it all tick is the equally sophisticated programming developed especially for traffic signal systems, the brains, the software. One command and control program developed by the Federal Highway Administration is the Urban Traffic Control System, UTCS, used in a number of cities throughout the country. Various systems firms have also developed programs and market them with their systems. These systems can be tailored to meet the needs of almost every community. UTCS is an online computer program that enables traffic signal systems to respond to real-time traffic demand in order to improve traffic flow on urban streets. Volume and occupancy data are gathered by detectors and transmitted to a central computer, where signal timing strategies are stored. From this library, plans are chosen that meet the changing traffic conditions reported from the intersections. From here, new commands go out to controller units to implement the program's timing strategies in near real time. Result: precise management of traffic flow in quick response to the realities of demand. Computer-based traffic control systems similar to either of FHWA's UTCS first generation, enhanced or extended systems can be expected to substantially improve traffic performance. Based on studies of 26 projects, an 8 to 25% improvement in average travel time can be achieved, depending on the quality of the signal system before the installation of the computer-based system. But even before new timing strategies are actually programmed and implemented, they can be evaluated at little cost through offline simulation programs like the FHWA's widely used network simulation model, NetSim. Without the trial and error of actual implementation, the traffic engineer can obtain a detailed evaluation of impacts for traffic control and design changes, such as turning movements, geometrics, channelization, signal timing, stop sign control, pedestrian control, location of bus stops and routes, and anticipate how proposed operational changes are likely to affect traffic flow. NetSim provides such quantitative measures of effectiveness as vehicle emissions, fuel consumption, stops and delay. Result: selection of the best alternative strategy evaluated in terms of the cost and potential risks of actual implementation of the strategy in the field. Another offline computer program, Transit 7F, aims to optimize signal timing for intersections along an arterial or network. It is widely used and has been tested throughout the United States in the FHWA's National Signal Timing Optimization Project. Eliminating manual procedures used to optimize signal timing plans, the Transit 7F model quickly analyzes such parameters as flow rates, minimum timing intervals, and turning movements, and produces optimized signal timing plans with specific figures for offset timing, cycle splits for phases, and performance measures for stops and delay. Estimates of fuel consumption enable the traffic engineer to select timing plans that minimize fuel consumption. Besides providing optimum signal settings, Transit 7F can model such conditions as the movement of buses and delays caused by pedestrians. The optimized timing plans produced under Transit 7F can be stored in computerized signal systems to be drawn on and implemented as needed. These are among the most prominent programs now in use. Other software packages can be obtained from other sources as well. What benefits can be gained from signal optimization, interconnection, and computer-controlled systems? 14 to 22 vehicle hours of travel time saved for every dollar expended. Signal system improvements are cost-effective for highway agencies and motorists. But regardless of the type of improvements made, even the most state-of-the-art system is only as effective and reliable as the extent to which it is maintained and the speed with which necessary repairs are made. How important is this? A recent survey in a major city showed that fully half of the traffic signals were not functioning properly, and that's not an isolated example. The maintenance department must have enough staff and budget both for preventative maintenance programs and for the capacity to respond to malfunctioning alerts and emergencies. How much is enough? That, of course, depends on a city's size, its particular physical layout, special traffic conditions, and other factors. For guidance on staff, budgets, and other key aspects of maintenance, look to the Transportation Research Board's NCHRP Synthesis of Highway Practice, Management of Traffic Signal Maintenance. It provides useful guidelines on the types of people needed, number of people required, other required resources, procedures, and liabilities. A key point to remember, as a changeover is made from an older to a newer traffic signal system, it's important to examine closely any new maintenance needs and, if required, to retrain maintenance employees. Fortunately, traffic departments can find plenty of help. The Federal Highway Administration, for example, publishes various handbooks and manuals relating to traffic signal systems and continually updates them. It also offers a wide range of specialized training courses. Other sources of information include FHWA's National Highway Institute and more than 20 technology transfer centers. We're a long way now from where we were in the old days of traffic signal systems, and still newer days are on the way as technology continues to advance. True, the problems are complex and keep on growing, but the technology is already there for the solutions we need. It needs only to be utilized. One thing is sure, for those whose job it is to keep things moving smoothly and safely at America's intersections, nothing ever stands still.